Hello everyone, welcome to AVLSI lecture number 10, part number 1. In today's session, we are going to cover the common source integrated circuit amplifier with PMOS diode connected load. In the last lecture or the last session, lecture number 9, we have seen that using a NMOS diode connected load over here, we have a body effect, and that brings out some non-linearity in the gain expression. So to avoid that non-linearity, we go for a PMOS diode connected load. So what do you mean by diode connected load? The transistors gate terminal and the drain terminal are tied together. So in this case, as you can see, M2 is the PMOS diode connected load, whereas M1 is acting as a driver transistor, wherein we have applied the input and the bias voltage, right? The bias voltage is not shown for simplicity over here. So this circuit, which consists of M1 driver and M2 load, is my common source amplifier with PMOS diode connected load. Fine. So this M1 NMOS transistor is my driver and M2 PMOS transistor is my load. Now, if you look carefully, both the transistors does not suffer from body effect, right? And well, what about the biasing conditions? M1 is biased at saturation, right? It has to, because we are making it work as an amplifier. And M2, any diode connected MOSFET, it's in saturation. So both M1 and M2 should be in saturation, right? Now let's see in details how VSB is 0 for both the cases. So over here, let's concentrate on this diagram, okay? And in an integrated circuit, the bulk or the body or the substrate, it's always connected to ground for NMOS, and its bulk is connected to VDD for a PMOS transistor. Fine. So this is the bulk terminal B2. It's connected to VDD, and the source is also connected to VDD. Now, since both source and body are connected to same potential, we say that the VSB is equal to 0. So M2 does not suffer from body effect. Now let's come to M1. M1, the body terminal is connected to ground. Source terminal is also connected to ground. Hence, no body effect. VSB is equal to 0. Okay, fine. So what we want next is, we want to derive a relationship between V out and V in. In a way, we want to find the expression of small signal voltage gain that is given by V out upon V in. So in moving towards that step, let's first find the impedance looking into the drain terminal of M2 transistor first. So once we find that Rx value, we can replace this diode connected PMOS load with a Rx, impedance. Fine. So we have splitted this circuit into two parts, and we are finding the impedance Rx seen into the drain terminal of M2 transistor. So let's derive it. So for a PMOS load M2, the small signal equivalent appear as depicted below. Yeah. So what do we have over here? We have VSB2 is equal to 0, correct? So let's try to draw the, I think this is slightly wrong. This is not correct. Yeah, something is wrong over here. Okay, sorry for the interruption. Actually, M2 transistor, the arrow was wrong. It should be pointed towards the, from the source terminal. So that was the mistake. Yeah. So now it's been corrected. Now let's try to draw the small signal model of a PMOS load. Right. So let's start. Now, since its VSB is not equal to, actually, it should be not equal to 0. Yeah, it should be equal to 0. Correct. Absolutely correct. Right. So over here we have from the gate terminal towards the source terminal, we have plus minus VSG2, right? And between the drain and source, we have GM2 into VSB2, and we have RO2. The transistor output resistance is also connected over here. So that's about the drain terminal. And if we wish to find the equivalent resistance from the drain terminal, right? So what we need to do is put the entire small signal model inside the box and externally applied a test source Vx and force the current Ix to it. So what will be Rx? Rx will be Vx upon Ix. Okay, and that's how we will proceed over here. Fine. So let me start. from the diagram, can we make a smart observation that VSG2 is equal to Vx, correct? And now what are we going to do is we are going to apply the KCL at the drain node, okay, at the drain 2 node basically. So what will happen over here is that we have one incoming current and two outgoing currents. What is the incoming current? Incoming current is Ix. If you see carefully, Ix is flowing through G2 and then it is going to D2, right? So Ix is equal to, now the outgoing currents, Gm2 into VSB2 plus Vx upon RO2. Now how does Vx upon RO2 has come? Now if you see carefully over here, Vx voltage is parallel to VSG2 and VSG2 voltage is in parallel with RO2 also. As you can see, they are both connected, gate and drain are connected, right? So between the gate and the ground and the drain and the ground, it's one and the same thing. So voltage Vx appears in parallel with RO2. Hence the current flowing through it can be written as Vx upon RO2. Fine. So if you apply a KCL at the drain node, what do we get? Ix is equal to Gm2 into VSB2 plus Vx upon RO2. So that's what we are getting, and we have already made an observation that VSG2 is same as Vx. So now we can club the terms of Vx together and Ix on the other side. So what do we get? What do we have over here? We can separate out open the bracket separately. So Vx into Gm2 plus Vx into RO2, divided by RO2. So Ix can be written as, the first term can be rewritten as Vx divided by 1 upon Gm2. It means Vx into Gm2 only. And the second term will be Vx divided by RO2. Now, if I have a comparison to this result, that is 1 upon R1 plus 1 upon R2 is equal to 1 upon R1 plus R2. Now, over here also the voltage Vx is common, right? And what is R1 signifying over here? 1 upon Gm2. And R2 is nothing but RO2. So hence we can write it the above equation as Ix is equal to Vx times 1 upon Gm2 parallel to RO2, right? And if we do Vx upon Ix, we will get 1 upon Gm2 parallel to RO2. Okay, that is your Rx. So Rx is giving the feel of two resistances in parallel. One of the resistance is RO2 and the other resistance is 1 upon Gm2. Fine. So this becomes our equation number 10.1.1, which is the exact expression if lambda 2 is non-zero. Fine. Now, normally your RO2 value is very much larger compared to Gm value. So if we assume RO2 is very much greater as compared to 1 upon Gm2, we can approximate the formula for Rx, expression for Rx. Now, Rx will be approximately equal to 1 upon Gm2. Now, this becomes the approximated expression if lambda 2 is non-zero, and the same equation 10.1.2 becomes the exact expression if lambda 2 is equal to 0. Because if lambda 2 is equal to 0, no way the RO2 will exist, right? So hence we can write Rx is equal to 1 upon Gm2 when lambda 2 is 0. Fine. So we have so far determined the value of Rx, right? So as you can see, we have determined the value of Rx. And now we substitute that value, replace the PMOS diode connected load with Rx resistance. So that's what we do over here, right? We found the resistance looking into the drain terminal. And now we can replace this PMOS diode connected load with this Rx resistance. And we know the value of Rx resistance. It's 1 upon Gm2. So when we replace it, we get a generalized form now. Rx is not externally connected. It's the diode which is presenting the resistance of Rx given by 1 upon Gm2. And now by inspection, we can easily say that the voltage gain AV will be given by minus Gm1 into RO1 parallel to Rx, right? Now you all have been given the flexibility to write it directly instead of solving it. But if you do solve it, you can do that. It's the traditional approach. So we have to draw the small signal model of figure number 10.1.1. Okay, so once we draw it, and yeah, so let's start drawing. Sorry for that. So to find the voltage gain of the circuit, we need to draw the small signal model of the circuit shown in 10.1.1. And we have done this many times. Now it's a mere formality for us. So the small signal model of the circuit is just the V out voltage is parallel to Rx and RO2. Hence the current flowing through Rx will be V out upon Rx. Current flowing through RO1 will be V out upon RO1. And over here, V in is equal to VGS1, right? So when we apply a KCL at drain 1 node, all the three currents are outgoing. So which are the three currents? GM1 into VGS1, V out upon RO1 plus V out upon RX. So now we substitute VGS1 as V in. So we get V in terms and V out terms in the same, we can isolate them, and after isolation we'll get V out upon V in is equal to minus GM1 into RO1 parallel to RX, right? That's actually the AV formula, right? Where RX value is given by 1 upon GM2. Now, if we substitute that value of RX, we get the small signal voltage gain of a common source amplifier with a PMOS diode connected load. And this is given by minus GM1 into RO1 parallel to 1 upon GM2. Now this expression becomes equation number 10.1.3. Now it's an exact expression if lambda 1 is non-zero. And if we assume RO1 is very much greater compared to 1 upon GM2, then we can write this formula approximately as minus GM1 divided by GM2. Now this becomes the approximated expression if lambda 1 is non-zero, and this AV becomes equal to minus GM1 upon GM2 if, or it's called as an exact expression if lambda 1 is equal to 0. Yeah. So now we know the value of GM because both M1 and M2 are in saturation, and the GM expression can be written as square root of twice mu and Cox W over L into ID. And from the expressions of from the circuit diagram, from the main circuit diagram, what can we observe? We can observe that the drain current ID1 is equal to mod of ID2. Correct? Because the PMOS, the same current flows to the PMOS and the NMOS transistor. Now let's proceed for the derivation. Sorry for that. Yeah. So what do we do? In the numerator, we have GM1 minus GM1, and denominator we have GM2. So how can we write the gain formula? AV will be equal to square root of twice mu and Cox W by L of 1 into ID1. And secondly, we can write divided by square root of twice mu and Cox W by L 2 into ID2. Actually, we should have written mod of ID2. So let's do that. So we can enter the value as mod of ID2. We'll replace ID2 from here because it's a PMOS device. Yeah. So now it's perfectly fine. So over here, let me just push it a little inside. Yeah. So from here, we know that the current ID1 and mod of ID2 is same, and your Cox value will be remaining the same, and root 2 will get cancelled out. So finally, after the assumptions and the approximations, the value of the small signal voltage gain for a common source stage or the amplifier with a PMOS diode connected load is approximately equal to minus of square root of mu n into W by L of 1 divided by square root of mu p into W by L of 2. So as you can see, the small signal voltage gain is only dependent upon the transistor sizes, that is W and L, and the mobility of the NMOS and the PMOS transistors, yeah, which are normally constant. So hence we say that the gain in case of a PMOS diode connected load common source amplifier is highly linear. Okay, so for every derivation, at least the circuit diagram and the final expression of the voltage, small signal voltage gain, should be noted down. Okay. So next, what do we do is, there are some important observations from this equation number 10.1.5. So first observation is that the gain, voltage gain AV, is not a function of bias current. There is no expression of bias current over here. So that means my amplifier becomes more linear. That means my changes in the input and output levels does not affect the gain. Also, it's not a function of voltage gain AV, it's not a function of input signal. That means as the input signal level vary, the gain remains relatively constant. That means my input and output characteristics for this amplifier is relatively linear, and that's a good news. Also, the gain AV is proportional to the square root of W by L ratios, transistor sizes, right? And the most important advantage over here is that the circuit is free from body effect, and we can add one more point, and non-linearity. Now, if you remember in the NMOS diode connected load, in the formula there was 1 upon 1 plus eta, which was bringing non-linearity into table. But this expression 10.1.5, there is no form of non-linearity present over here whatsoever. And your gain of your circuit is a high level of linearity is achieved using PMOS diode connected load. Okay. So I'll keep this window open for some time so that you can have a look at the observations. Fine. Let's proceed forward. Okay. We can rewrite the expression of 10.5.1 that is AV is equal to minus GM1 upon GM2 as GM can be written as twice ID divided by, alternatively written as twice ID divided by VGS minus VTH, right? So, and also ID1 is equal to mod of ID2. That's we know. So AV, after simplifying, twice ID1 and twice mod of ID2 will get cancelled. And finally, you will get the formula of small signal voltage gain alternate expression as approximately AV is approximately equal to minus of VSG2 minus mod of VTH2 divided by VGS1 minus VTH1. So alternatively, this is also the expression for small signal voltage gain of a common source amplifier with a PMOS diode connected load. Fine. So have a look at it, what we have done, and then we will proceed to the next topic. Okay. So let's move forward. So there are some advantages and issues or the problems associated with common source amplifier with diode connected load. So first advantage over here is that your gain AV remains constant with the input variations, which will lead to linearity, and that's an obvious advantage. Next, the voltage gain is not a function of bias current. That's also we have seen in the observations from the equation number 10.5.1. So this is also an advantage. Gain AV is higher compared to other other loads, like you can say resistive load, current source load, diode load, and even for that matter NMOS diode connected load. So their voltage gain is higher, and it's precisely set by the transistor sizes. Additional biasing for M2 is not required over here. Okay, you remember for a current source load we require a external biasing for M2 VB, but that possibility is not be required over here. So we have a reduced silicon area size. That's an advantage. But one disadvantage over here is that it has a lower voltage swing. The output voltage swing is not from 0 going up to VDD. No, it's not that. So we have a reduced voltage swing, which is a problem. Then the body effect reduces AV, or the AV, that is the gain in case of NMOS diode connected load. So we have talked about this before. In an NMOS diode connected load, because of the body effect, the voltage gain is slightly reduced. And yeah, one more thing is there. This problem is associated with both NMOS as well as PMOS diode connected load. That is, a load transistor M2 offers static power dissipation. That means since your M2 is continuously on, irrespective of the input, there will be existence of static power dissipation, which is pretty bad when we are considering the fabrication on a integrated circuit. Okay, so these are the points of in favor of common source amplifier with diode connected load, and some points are hampering the performance of your common source amplifier with diode connected load. Fine, so I'll keep it steady onto the screen, you can have a look at it. Okay, so I guess we have covered the topics which were meant for AVLSI lecture number 10.1, and let's revise what we have done. So first of all, we have derived the expression for the voltage gain for PMOS diode connected load common source amplifier, and next we have seen the dependence, how the gain is independent of the signal variations. We have made some observation based on the final small signal voltage gain formula, and also we have seen some of the advantages and disadvantages of using a common source amplifier with a diode connected load. So we have come to the end of this session. That's all from lecture number AVLSI lecture number 10.1. Next time we will start with AVLSI lecture number 10.2, that is comparison of common source amplifier with different loads. So until then, have a good day and thank you.